Get ready for a game changer in the world of generative AI and materials science. A new tool is set to revolutionize the way we create breakthrough materials, and it's an exciting development for researchers and enthusiasts alike. You see, the AI models that can turn text into images have a hidden talent. They can also generate new materials. Over the past few years, these models have been quietly helping researchers design millions of new materials, but there's a catch. When it comes to designing materials with unique quantum properties, these models struggle. And that's a big deal because humans need all the help they can get in this field. Take the example of quantum spin liquids, a class of materials that could revolutionize quantum computing. After a decade of research, only a dozen material candidates have been identified. It's a bottleneck that limits our ability to make technological breakthroughs. But fear not, because MIT researchers have developed a technique that's like a secret weapon for generative materials models. It's called SCIGEN, and it's all about following specific design rules. These rules, or constraints, guide the models to create materials with unique structures that exhibit quantum properties. The models from large companies focus on stability, but that's not always what we need, says Ming-De Li, MIT's class of 1947 career development professor. We only need one really good material to change the world. The researcher's approach is described in a paper published by Nature Materials, and it's a fascinating read. They applied their technique to generate millions of candidate materials with geometric lattice structures associated with quantum properties. From this vast pool, they synthesized two actual materials with exotic magnetic traits. The quantum community is interested in geometric constraints like Kagome lattices, which are like two overlapping upside-down triangles, Li explains. These materials can mimic the behavior of rare earth elements, making them technically important. The team's technique, SCIGEN, is a computer code that ensures diffusion models adhere to user-defined constraints at each step. It's like giving the models a set of rules to follow, allowing users to guide the generation process. To test SCIGEN, the researchers applied it to a popular AI materials generation model, TiPdBi. They instructed the model to generate materials with Archimedean lattices, which are collections of 2D lattice tilings of different polygons. Archimedean lattices are known to lead to a range of quantum phenomena and have been a focus of research. Archimedean lattices give rise to quantum spin liquids and flat bands, which can mimic rare earth properties without the elements themselves, says Muyang Cheng, a co-corresponding author. Some of these materials have large pores that could be useful for carbon capture, so they're a special collection. In some cases, we might even discover the first material to fit a specific lattice. The model generated over 10 million material candidates with Archimedean lattices, and after screening for stability, they were left with 1 million. Using supercomputers, the researchers then simulated the behavior of 26,000 materials, finding magnetism in 41% of the structures. From this subset, they synthesized two previously undiscovered compounds, TiPdBi and TiPbSb, in labs at Michigan State University and Princeton University. We wanted to discover new materials with huge potential by incorporating structures known to exhibit quantum properties, says Ryotaro Okabe, the paper's first author. Starting with these specific geometric patterns is a natural approach. This new tool has the potential to accelerate the discovery of quantum spin liquid materials, which could unlock the potential of quantum computing. It's a necessary step towards finding stable, error-resistant qubits that form the basis of quantum operations. There's a big search for materials for quantum computers and topological superconductors, and it's all about the geometric patterns. Says Weiwei Shi, a co-author, experimental progress has been slow, but SCIGEN can generate many materials that satisfy the necessary constraints, giving researchers more candidates to work with. Steve May, a professor at Drexel University who is not involved in the research, praises the work. This tool, leveraging machine learning, can predict which materials will have specific elements in a desired geometric pattern. It should speed up the development of previously unexplored materials for next-generation technologies. The researchers emphasize that experimentation is still crucial to assess the feasibility and properties of AI-generated materials. Future work on SCIGEN could incorporate additional design rules, including chemical and functional constraints. People who want to change the world care more about material properties than stability and structure, Kagome adds. Our approach might reduce the ratio of stable materials, but it opens the door to a whole new world of promising materials. This work was supported by the U.S. Department of Energy, the National Energy Research Scientific Computing Center, the National Science Foundation, and Oak Ridge National Laboratory. And there you have it, a new tool that's set to make waves in the world of materials science. It's an exciting development, and we can't wait to see the breakthroughs it enables. What do you think? Will SCIGEN revolutionize the field? Let's discuss in the comments.